All right, so far these words here, sample space is probably the one that we are not most familiar with, right? Sample space is the set of all possible outcomes. So if I put the numbers 1 through 20 in a hat, okay, what would the sample space be? Well, it would be a collection of all of the possible outcomes. If I'm going to draw one number, then I could get 18, right? And that would be an outcome. What would be another outcome? 2. What would be another one? 1. Okay, now if we wrote all of them down, that's called the sample space. It's the set of all possible outcomes of an experiment, okay? And then an event is a sub-collection of the sample space. So we'll write that down here. A sub-collection of the sample space. And I'm going to use SS for sample space. That's an SS. Okay, so this is where our talk about probability begins. We're defining a couple of the keywords here. So we have to understand experiment, outcome, sample space. This is probably the most important one. And then event. Okay? Experiment, outcome, sample space, and event. You guys ready to go on? Okay. So we're going to find the following sample spaces of these 3 experiments. Okay, we have some experiments here. The experiment would be sort of tossing a coin, all right? The sample space, then, SS for sample space, is going to be the set of all possible outcomes. If I toss a coin, what is one outcome I could get? I could get heads. What's the other outcome I could get? I could get tails. Can I get anything else? I cannot get on the edge. I know you guys always think the edge. I cannot get it on the edge, okay? All right, we don't live in the crazy universe. If I'm tossing 2 coins, the sample space, I'm going to toss 2 coins. What's one possible outcome for tossing 2 coins? Head, head. Head, head. What's the next possible outcome?
Head, tails.
Head, tails. What's another possible outcome?
Tails, tails.
Tails, heads, and then tails, tails. All right? I want to take this opportunity right now to show you how the fundamental counting principle plays a role in this, okay? If I'm going to toss one coin, how many different ways how many different outcomes are there?
2.
There's 2. Notice that I have 2, a head or a tail. I'm going to toss 2 coins. Okay, coin number 1 and coin number 2. I could get a head or a tail, so I have 2 out there. I could get a head or a tail, I have 2 there. The fundamental counting principle says we multiply them together for a grand total of 4. Check it out. There's the 4 different outcomes, okay? So you really have to understand the fundamental counting principle. It comes up all the time with probability. Okay? Now, let's find the sample space for tossing 3 coins. The sample space, okay? Before we begin, ladies and gentlemen, let's use the fundamental counting principle to guide our thinking here. Okay? Coin number 1, coin number 2, and coin number 3. How many outcomes for the first coin? How many for the second? And how many for the other one? So therefore, fundamental counting principle says I should have how many in my sample space? There you go. Love it. What's up, buddy? So this should just be S sample space. Sorry, dude. Yeah. I don't know. I don't like that. Let's make it, there we go. Better. Okay, sample space. Sorry. There we go. The sample space, not SSS. You know why? It's because I'm doing this. One outcome would be head, head, head. That's an outcome, right? That's why I have 3 there. Okay. What's the other outcome I can get? Head, head, tail. Head, head, tail. Give me another one. Head, tail, head. Good. Give me another one. Tail, tail, tail. Okay. Give me another one. Tail, head, head. Good. Give me another one. Tail, tail, head. Give me another one. Head, tail, tail. Yep. Last one.
Tail, head, tail.
Tail, head, tail. And the fundamental counting principle says that's how many there are. I can't get any more, so my sample space has 8 things in it. It's the collection of all the outcomes, okay? So we're just getting good at talking about the language of probability. So the definition of probability for us, we're going to say this. The probability of an event E is equal to the number of ways the equally likely events can happen over the grand total number of things in your sample space. Okay? So let me give you a little easier definition. So this is ways something can happen over the total. Total in the sample space. Okay? So the sample space is very important. That's going to be the denominator of our probability. The sample space. The size of our sample space will be the denominator of probability. A couple of key things here. Okay, 0 has to be less than or equal to the probability of whatever your event is, less than or equal to 1. So that means that your probability is a decimal, also known as fraction between 0 and 1. Okay? If the probability of your event is actually equal to 0, what do you think that implies, you guys? That implies it's not going to happen. Okay? And I realize I'm putting the word gonna on a pen. Okay, not going to happen. So, can you guys think of something that the probability is 0?
The sun sets in the east.
The sun sets in the east. Okay, what do you guys think about that? Is that good?
Wait,
Unless you're...
here. Anything could happen.
All right. How about this? What's today? What's today? Friday? Okay. The probability that tomorrow is Wednesday. That is not going to happen. Okay. So that's 0.
That's when we change it.
Okay. Yeah, that's not going to happen. Okay.
And that's when we change the calendar.
All right. What's the probability? If the probability of your event, let's go to the other extreme, is equal to 1, what does that imply? It's going to happen. Okay. So if today's Friday, probability that tomorrow is Saturday is 1. That is going to happen. Okay. And then last little note to know here. The sum of all the probabilities of your event have to add to 1. So what do I mean by that? The sum of all probabilities adds to 1. Well, here, let's go back up to this one really quick. And let's talk about tossing 3 coins, okay? What would be the probability of getting head, head, head? Well, the probability would be, the way that it could happen is 1 out of the grand total of 8. So the probability of getting head, head, head would be 1 out of 8. Now, what's the probability of getting head, head, tail?
1 out of 8.
So are these equally likely events?
Yes.
What would happen if I added up 1/8 8 times? What would I get? I would get 1. So the sum of all probability events is added to 1. Does that make sense? You guys on board with that part? Okay, cool. All right, here we go. More examples here. Kind of fun. One's kind of straightforward here. First thing we want to do is we want to get our sample space for tossing 2 coins. Well, we already did that, right? We did head, head. We did head, tail. We did tails, head. And we did tails, tails.
Do we have to do that every single time?
You have to define your sample space, yeah. So tossing 2 coins and getting 2 heads. Well, that's 1 out of what? Yeah, 4. The probability of getting a head, head is equal to 1 out of 4. All right, there's one way that could happen. There's 4 total in our sample space. The probability is 1 out of 4. All right, let's say choosing an ace from a deck of cards. How many cards in the deck? 52. So the probability of getting an ace, okay, the grand total is 52. That's, I don't want to write that sample space down. That's a big sample space, right? I would not want to write that one down, okay?
So what would we do in order to show work for the sample space?
You put it on there on the bottom, 52. You tell me that there's 52 in there, okay? How many aces are there in the deck? Yes? There are 4 aces in the deck. There's the ace of spades, diamonds, clubs, and hearts, right? So therefore, we can simplify that fraction to 1 out of 13. The probability of pulling an ace is 1 out of 13. Yes, sir. Okay, I like this one too. Tossing 2 fair dice and ending up with a sum total of 7. Well, has anyone ever heard of lucky number 7? Like, they say 7's a lucky number, okay? Okay. And I wonder why they say 7's a lucky number. So,
They're the most possibilities.
that's the most possibility. It's not really lucky. There's just more of them to pick, okay? So think about this. Talk about it in your groups, and then we'll discuss. Awesome. So would you guys agree that the sample space then could be categorized by this little chart here, right? This would be dice number 1 and then dice number 2, right? So let's see here. Let's put a little X mark on all the ways. Let's say if this is dice, if I roll a 1 the first time, what would I have to roll on the second die to get a sum total of 7? A 6, right? If I rolled a 2, I'd have to roll a 5. If I roll, do you guys see a pattern here?
Yeah.
Okay, good. So check this out. So all these X's right here, they represent all the ways I could get a sum total of 7. You guys agree with that? So how many ways is that? So that's it. So the probability of rolling a 7 would be all the ways we could get a 7. There are 6 of those ways. They're right there in the x's. Out of, if I multiply these together, right, what do I have here? I have a 6 by 6 grid, so a grand total of what? 36, so therefore, my probability is a 6th. Now, the reason 7 is the luckiest is because it's the main diagonal. It shows up the most amount of times, right? What are the ways I could get a sum total of a 2? Yeah, there's only one way I could get a sum total of a 2. There's only one way I could get a sum total of a 6, too. Or 12. So the probability of rolling a 12, sum total of 12, is way less probability of rolling a 7. That's why 7 is the lucky number 7, only because it shows up more. Not really lucky. There's just more of them on the table. Check it out. Let's figure out the probability of winning the California Fantasy 5 Lotto. All right, now
Isn't it like something in the billions?
I want to point something out to you guys, right? As I was making this lesson, I'm like, this is kind of be fun to figure out. I wonder if we can actually get the right answer. So I go onto the internet, and of course, where everything lives, and I go step 1. These are the directions from the internet. Step 1: find a retailer close to home, work, or your favorite coffee shop. So really, step 1 is like literally go to the store and buy a ticket. Crack me up. Okay. Step number 2, the thing that we actually really care about, you have to pick 5 lucky numbers from 1 to 39 on a Fantasy 5 play slip, or play randomly generated numbers with a quick pick. So there it is right there. This is how you play. You get to pick 5 of 1 through 39. Go ahead and figure out the probability of winning. So we were just talking about this, and I want to show you what I pulled from the website. Okay, this is what I pulled from the website. Check it out. The Fantasy 5 odds. The odds that you win are right there. 1 in 575, 757. Okay? So let's go back here for a second, and let's talk about what you guys did. First of all, how do they get 575, 57, whatever they got? How do they get that? Yes. Okay, absolutely. So from the 39 numbers, we want to combine any 5 of them. It doesn't matter the order in which you pick the numbers, because they all end up in the same order on the ticket anyway, because the machine puts them in numerical value from lowest to smallest. But it doesn't matter what order they're picked, right? Because if, say, our winning what was it? What did I have? Let's say I had 1, 5, 8, 9, and then 11, right? Those are the winning numbers. Well, in the very first pick, 8 pops up. In the very next second pick, 11 pops up. And then the 5, and then the 1, and then the whatever, right? So the order in which they are picked does not matter. Just the grand total of having all the numbers on the ticket matters. That's a combination problem, right? So therefore, the probability of a win is 1 out of 39 choose 5. And the reason it's 1 up there is because there's only one combination, right, of those numbers out of 39 choose 5. I see your hand. 1 second. What you guys did was this. You guys did 39 times 38 times 37 times 36 times 35, right? Is that what you guys did? Okay. What is that actually doing? That's putting them in a certain order on a shelf. That's what that's doing. That's different than choosing 5 in any random order, okay? That's different, okay? Okay. So you guys were right. And I have verified that you are right because I pulled this straight from the website right there, okay? So you got 575, 757. All right, we talk about mutually exclusive events because we have to talk about events that overlap, all right? So 2 events, so we'll call events, so we'll just say 2 events are mutually exclusive. I'm going to use ME for mutually exclusive. If they share... They have, we'll say it this way, no outcomes in common. Okay? So, as an example, choosing a red club, those 2 events are mutually exclusive. There's no way that you could choose a red club from a deck of cards. Okay? They're mutually exclusive events. Okay? So we would say this. So if A is an event and B is an event, and they are mutually exclusive, then the probability of getting A and B, this is the way we say this is the intersection, okay? This is the intersection.
Oh, and then is the one that's U, that's the...
Yep, that's OR.
That's
this is equal to 0. So if your events are mutually exclusive, then the probability of getting A and B together is 0, which means it's a totally unlikely event. It cannot happen. So the probability of the union of events, so let's say again that A and B are events in the sample space. Okay, these are events. So let's say the probability of getting A or B. The way that we get this is, the way that we say it, excuse me, is the probability of A union B. So this part means A or B. When you see the little U, that means or. It also means union, okay? That's equal to the probability of whatever A is plus the probability of whatever B is minus the union of the two, probability of, or sorry, the intersection of the two, A and B. So let me give you an example. Okay. So let's say, before this, one more thing to add to this. Okay, if A and B are mutually exclusive, then we say this: the probability of A union B is just probability of A plus probability of B, because this part would be 0 if they're mutually exclusive events. Does that make sense? You guys have known that?
Wait,
All right,
let's
talk about this, okay? What's the probability that you draw a heart or a face, okay? So think about this. Is this event mutually exclusive, yes or no?
No.
The answer is no, it's not, because you could draw a heart that is a face card, right?
Yeah.
Okay, so these are not mutually exclusive events. So here's what we're going to do. Here's our example. So we want to figure out the probability of getting a heart or a face. Do you guys agree with what we're trying to find? Heart or face? Probability of that. Well, according to our problem, we're going to have, that's going to be the probability of getting a heart plus the probability of getting a face minus the overlap, right? Because there's a certain amount of overlap between hearts and faces.
So, like, how many faces can be hearts?
Exactly. Minus the probability of getting a face, a heart and a face.
And is upside down here, right?
Yep. The intersection of the two.
Okay, I have a question. So in
Okay? Okay, guys, what's the probability of getting a heart?
113.
How many hearts are there? Well, I'm going to say 13 out of 52 to keep my denominators the same. You guys agree with that? Okay, the probability of getting hearts, 13 out of 52. What's the probability of getting a face?
There's 3 faces for each.
12.
12 out of 50.
Yeah, there's the king, the queen, and then the joker, right?
And that's for each.
I mean, not Jack, Joker. I mean, yeah, Jack, sorry. Joker, yeah. So Jack, king, and queen, right? So there's 3 face cards for every suit, and then there's 4 suits, so there's 12, right? You guys read that? Okay, so this is 12 out of 52. But some of those face cards are hearts, right? So we got to subtract off the overlap. So how many face cards are hearts? 3 out of the 212, 52. You guys on board with that?
okay.
Are you guys cool with that?
Wait, I need to learn cards.
Okay. So therefore, I have this. I've got 13 plus 12 minus 3 out of 52. So what is that, 25 minus that, 22 out of 52? And I'm going to leave it as a fraction like that. So the probability of getting a heart or a face is 22 out of 52. Yep, or 11 out of 26. That would be good too.
Is that just the answer?
Yeah, that's our probability of getting a heart or a face. Okay? So that means that this event right here, these events not mutually exclusive because their intersection is not 0. Okay? All right. We're almost done. I need all this time here. We're talking about and versus or. This is a very, very fast box. Okay? The word and means multiply. The word or means add. There you go. That's the whole box. Okay? And means multiply. Or means add.
That was great. And last box.
You think it's the
Yeah, you think it's the opposite, right? But it's not. Okay, here we go. Love this example. Here it is, okay? I have 3 beautiful, colorful spinners for you, all right? And here's what I'd like you to do. Let's determine this. What's the probability of spinning a B or a D and then a 3? So we're going to spin this one first, then we're going to spin this one, right? And we're gonna say that the probability of landing on the line is 0. So it'll always be a 1 or 2 or 3 or an A, B, C, or D. So what's the probability of getting a B or a D and a 3? That seems really hard, but we are smart because we understand the difference between and or. So here we go. What's the probability of getting a B?
1/4.
1/4. What's the probability of getting a D?
1/4.
Also 1/4. What's the probability of getting a 3?
1/3.
1/3. So B or D or means what?
1/4 times.
Or means add.
equals
So
1/4
1/4 plus 1/4 and means
1/3.
multiply. So 1/4 and 1/4, how much is that?
1/2 times 1/3.
1/2 times 1/3 is?
1/6.
There you go. How easy is that? Okay. All right. Do part B on your own right now. Tell me what you get right there.